Hi students, this is Mr. Yao. Today we're going to talk about 3.3, the third lesson for key features of functions. We're going to learn about domain, range, and behavior, and some evaluation. So first, some prior knowledge. Last year we have learned that a relation is a set of ordered pairs that can be expressed as a mapping, a table, a graph, or a description. A function has a very specific definition. It is a set of ordered pairs which each x can be matched up with only one y. This is what makes it as a function, makes a relation as a function, only one y. We typically call x as input, or more mathematically, independent variable, and we typically call y as output, or more mathematically, dependent variable. So x is independent because we typically change our x, that's the input. Then the result that follows are depending on our x. That's why the y is dependent variable. Now the definitions for today's items. Domain and range. Domain, all the possible x values, or input, or independent variable. And when you read on the graph, here are the important things. You gotta read from left to right. Just like how we read a number line, or how we read the increasing, decreasing, positive, negative stuff from last lesson, left to right. For the range, it's all the possible y values, or the output or dependent variable, and this time when we read y, it's bottom to top. Or you can think of it as it's from negative to positive. Because on the number line or on the x-axis, left side is negative, to the right is positive. For the y-axis, the bottom is negative, to the top is positive. Now let's look at a review example. We're given 5 ordered pairs, and that means it's a relation. It's a function. So we're going to actually write it in tables. We just need to list all the ordered pairs, -5 and 2, -1 and 4, 0 and 1, 2 and 1, and 4 and 4. Now the mapping. Mapping, basically we have an x and a y. For the x, we're going to list all the x values, -5, -1, 0, 2, and 4. Here's a way to think about it. It's called a mapping. That means each number has a place, a location to go to. So when we list all the y's, we have 2, 4, and 1. Then you see this 1 is repeating. Then you see this 4 is also repeating. And because that means these y values means all the x numbers are going somewhere, well, if you're thinking about a house, you can't exactly say there are 5 people going to that house. That means there are 5 houses in that same location. It is still just one house. That's why we do not write the repeats. -5 is being mapped with 2, -1 is being mapped with 4, 0 is being mapped with 1, 2 is being mapped with 1, and 4 is being mapped with 4. And as you can see, each person can actually go to one house. But each house can, of course, take more than one person. But no one is actually going to 2 different houses. That wouldn't work. If I actually have this, that wouldn't work. That would make it not a function. Each person can only go to one house at a time. As for the graph, we're going to just graph all the points, -5, 2, -1, 4, 0, 1, 2, 1, and 4, 4. Now let's write the domain. Domain will be the x values. For these domain and range, you do need to make sure you're writing from smallest to largest. So -5, -1, 0, 2, 4. Because we have listed every single possible number, there's nothing else that's not included. We have listed every single thing. Like we have written them out. So we're going to use curly braces because these are just single numbers. So we're going to use domain as curly braces. For range, smallest to largest, 1, 2, 4, inside curly braces again. So again, whenever you can write down every single value for the domain and range, we're going to use the curly braces because that means it's a set. Or in other words, it's a discrete relationship. That means everything is separated. Next. When we deal with more complicated domain and range questions, we're going to use a technique called a squash technique. We're going to squash the graph onto the x-axis because that means all the values are going to be on the x-axis. So that's the domain. Or we're going to squish everything onto the y-axis, so that means everything is going to be on the y-axis, so range. Now let's have a look at how that works. Example 1. First, in order to find a domain, I'm going to squish everything onto the x, so we're going to squish this way, so that all the numbers are going to end up on the x-axis. So this point is being squished right there. This point is being squished right there. This third point is squished onto the x-axis right there. This right here. The last one is already on the x-axis, that stays there. So these are the points we're writing for the domain on the x value. So it's going to be -5, then -3, then 0. Again, this point right here, that's 0 between -1 and 1. And then 2, and then 5. Because we have listed every single thing and they're all just points, we're going to use curly braces. As for the range, this time we're going to squish the other way. So this point, again, when you squish for the y-axis bottom to top, this point goes right there. This point being squished to here, this point being squished to here, and that point is being squished to here along with the point already on the y-axis. They're going to stay there. So now for range, I'm going to write from bottom -3, then -2. This point is 0, and this point is 4. Inside curly braces, because these are just single points, and I have listed every single number. That's example 1. Now let's have a look at example 2. Squish again this way. So here's something you need to be very clear with. These lines, they're arrows. That means it actually goes on forever, even outside the graph. Even outside the graph. So when you're actually squishing, there are points even outside the graph onto the x-axis. Squishing, 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 squishing. I have all of these points. I have all of these points on the x-axis, and they're actually all connected. Here, squishing, 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 keep on squishing, and they keep on going even outside the graph. So that means all the points that I have on the x-axis start all the way from the left, which is -infinity, to all the way on the right, which is +infinity. And then for the range, it's going to be the similar idea. I'm going to start squishing right here onto the y-axis, so I got more points. So on the bottom, there are more things. Keep squishing, keep squishing, keep squishing, keep squishing. I have more things. Squishing, squishing, squishing. I even have things outside the graph. I have a lot of y values, start all the way from the bottom onto the top. So -infinity to +infinity for the range as well. Next, example 3. Same idea. Squish this way. However, this time it's slightly different. This and that is not an arrow, that is a point, which means I do not have anything to the left of that point. So when I squish, this is the first point being squished onto the x-axis, so right there. Keep squishing, I have more things, I do have more things. Okay, I still have all of these points. And the right side, you can see an arrow, that means to keep on going. So I do have more things even outside the graph. So for my domain, when I look at my x-axis, I start from this very point right here, -5, all the way to the right to infinity. Infinity, of course, that's parentheses because we can't exactly reach infinity. We don't know what number it is. -5 is a solid dot. That's why I'm going to use square bracket. If I have this as like an open circle, then that would actually be parentheses for -5 as well. Next, I'm going to squish the other way. So for this graph, it's a little bit special. When I squish the other way onto the y-axis, there's nothing below. There's nothing to squish. Until you reach this very point, you have something to squish. So that means I start with my 0. And then I'll start squish my left side first. Squish onto the y-axis, I have all of these points until I'm right here. So it stopped. So on the left side, this is the last point I got. However, when you check the right side, I do have a lot of stuff. But I actually keep going. I actually keep going up. And since I'm only reading for numbers I have on the y-axis, I still have points even above this point I just drew. So I have more things, and it goes to infinity. And since at 0, this is a solid dot, I did actually end up squishing it onto the y-axis with a solid point. That's going to be a square bracket. So that's example 3. Next, example 4. Same idea. Let's actually have a look at the domain and range again for 4 and 5. So the domain, well, that's an arrow, so it means it keep on going forever on the left and forever on the right. So we write the domain and range. Well, everything has a number that you can squish onto the x-axis, so negative infinity to positive infinity. And for the range, well, same thing. We do have things for all the x, all the y. So it's negative infinity, positive infinity again for the range. Number 5. This time when you squish on the x-axis, well, this side is easy because it's an arrow, so we do have a lot of things starting from the left side. They are all getting onto the x-axis, so starting from negative infinity. However, if you keep going, keep squishing, you will realize there's a solid point right here. It's not an arrow, so it doesn't go any further to the right than that. So this is the last point I will squish onto my axis, which is 8. Since it is a solid dot, square bracket. As for the range, I have everything squishing onto here, onto the y-axis from the bottom, so negative infinity. As for the top, squish, squish, squish. My very last point is right here. And this number right at that point, that is 10. I'm still going to use square bracket for that. That's the domain and range for number 4 and 5. Now let's also look at something called the end behavior. End behavior is how a graph acts or behaves on either side. For this year, we will specifically learn about what happens when the graph goes all the way to the left and all the way to the right. So we're indicating when the graph actually never stops. So we have an option when it does stop. That most likely may be something called not applicable or does not exist. So let's have a look at the notation for this. We have, because every single graph we see, we basically have 2 different ends. So we have this end, and we have that end. We have a left end and a right end. When x goes to negative infinity on the number line is on the left. So that's indicating I'm looking at the left end, the left tip. So you can see our graph is going up left. Again, as I described, that's up left, which means when my graph goes to the left, it's also going up. So the x indicates it's going left. The f of x, which is also the same as y, that is going up. So that is going up to infinity. Now the other one, going to the infinity, that's the right, because that's going to, the infinity is on the right side. So that means I'm looking at my right end. My graph keep on going down, right. So that means when I'm going right on the graph, I'm also going down to negative infinity in this case. So the last one, f of 0, that means you're looking for the value where x is 0. So x0 is right here on the graph. The point is right here at 1. So you're just identifying what is the y when x is 0. So again, what is y when x equals 0? This is the x equals 0 part. So that's the full-on example 4. Now let's have a look at example 5. As x go to negative infinity, so that's the left side. So that means I'm looking for my left tip is going down. So when I'm going to the left is going down, that means going to negative infinity. And we're thinking about going left forever. And then which other direction is also going? It's also going to negative infinity because this is our y. For the other one, when it's going to infinity, that means going to the right. We're looking for the right tip. However, my graph actually does not go to infinity. It doesn't actually go to infinity. Then of course, on the vertical, on the y direction, it's also not going to any infinity or negative infinity. So it's going to be called not applicable or does not exist. Either one works. Then f of 8. F of 8 is right here. I do have a value for that. So when x is 8, my y is 10. So when x equals 8, that's what I'm looking for. My y is 10. So f of x equals 10. That's example 5. Now let's have a look at more examples. Number 6. Domain first. That means I'm dropping everything onto the x-axis, so starting from here. This is different from example 1 because example 1 only has points. This, we have all of these connection lines. So we're going to need to drop even those line parts. Everything is going onto the x-axis. So my very first point is right here, starting from -3 and going all the way to 3. Since they're both solid dots, they're going to be square brackets. For the range, same thing, -3 to 3, because when you drop them onto the y-axis, right here, first point is -3, keep on dropping, keep on dropping, keep on dropping, keep on dropping, and here I even have things dropping on from the left end, but no matter what, the highest point I got is at 3, so -3 to 3. As for negative infinity and positive infinity, my graph does not even go to infinity because these are solid dots, they're not arrows. That means there's for end behavior is NA or DNE. It's NA or DNE. And f of -1 is going to be right here at -1. This is the point I got right here at 2. So when x is -1, my y is 2. That's example 6. Now example 7. Domain. You do need to be very clear on the graph. My graph is going forever on the left and forever on the right. So when you actually start dropping things onto the x-axis, that means I have all of these points to the left, all the points here, and all the points to the right, and keep on going, even outside the graph. So negative infinity to positive infinity. As for the range is going to be nothing here, nothing here. When I squish onto the y-axis, this is the first point I got at -3. And then I keep squishing, keep squishing, keep squishing. I got more things on the right, on the top, and I keep on going forever. So to infinity. Infinity is always parentheses. At -3, I do have a solid dot, so square brackets. As for the end behavior, by the way, these may not actually be given on your notes. That's because I'm giving you 2 for 4 and 5 as examples. But for example, 6, 7, 8, and 9, you are going to need to write these because you're going to need to practice how to actually write these in the right format, in the correct format. So as x go to negative infinity, that means I'm looking for the left tip again. My left tip clearly is going up left. So it's going up left. As I go to left, it's also going up, so infinity. And when it's infinity, that means I'm looking for the right tip, which is right here. It means that my graph, when it's going right, is also going up to infinity. And last thing, f of -2. f of -2 is actually right here. The point is right there at 1. That's example 7. Now example 8. Domain is pretty easy for this one. Because my graph, you can see, keep on going left, keep on going right. So the domain, if I drop everything onto the x-axis, I do have numbers, negative infinity to positive infinity. However, the range is slightly different. If you remember, when we first talked about this graph as the exponential graph, the range, it actually never touches whatever line you see right here. It never touches that line. That line is at the value of 0. So that means we still need to include 0. We still need to write the 0. The only thing is all the numbers are just slightly above 0 and never touches 0. Then all we need to do is not include 0. So we use parentheses to indicate 0 is not included. But anything that is even slightly bigger than 0 are included. So we keep on going, keep on going. You can see the graphic still has more things to drop on the y-axis. Keep on going forever to infinity. As for the end behavior, this is also special. So as you can see, as what we just said, when my graph is going to the left, so this negative infinity is going to the left. When my graph is going to the left, it actually never crosses this 0 line. So it's getting super, super, super close to 0, which means my y is actually getting to 0. It's just never get there, but it's getting super, super, super close to 0. So that's the end behavior on the left side for this. When it's infinity, that's the right side. You can see it's going up right. So that means when it's going to the right, it's also going up to infinity. As for f of 2 is right here at 4. Now example 9. Because my graph starts all the way on the left, 2 all the way on the right, the domain doesn't change, negative infinity to positive infinity. The range, if you start dropping, there's nothing here, nothing here. The line that is close to touching is right there at 3. So that means my range will start from 3, because I do have everything above 3. They're all getting onto the y-axis to infinity. And again, to make sure we're not touching that line, we're not going to include the 3, so parentheses. As for the end behavior, on this one, for this side is going up left. So whenever it's going left, it's going up. Negative infinity means I'm looking at my left end. My f of x is going up to infinity. Now, if you look at the right end, it is approaching this 3 and getting super close to it. So when x is going to infinity, my f of x is getting super close to the 3. So that's the end behavior on the right end. Now, f of -1. F of -1 is right here at 5. That's example 9. Now, the last few things, we are going to learn how to evaluate some functions. All we need to do is something called plug in. So for this number 10, g of 2, that means wherever you see the x, you're going to replace it with a 2. My suggestions, make sure you put it in parentheses. This is really important. Make sure you put it inside parentheses. 2 times, that's a 2 plus 5, which is 4 plus 5, so 9. Number 11, h of -3. So that means I'm replacing the x of -3. Again, put it inside parentheses, then square it, -1. So this is basically -3 times -3. If you're typing your calculator, that's going to give you a positive 9 minus 1, which is 8. Next, example 12. I'll rewrite this 9 right here. So f of -5, that's absolute value of -5. I'm just replacing the x. Again, whenever you see x is a -5 plus 4. Absolute value makes everything positive, so that's 5 plus 4, which is 9. Number 13, h of -1. So -1 plus 3 minus 7. Just replacing the x with -1. -1 plus 3, that's a 2. So absolute value of 2 minus 7, which is 2 minus 7, which is -5. Now, example 14. I'm just replacing the a with 1/5, so w 1/5. -5 fourth is multiplying by an a, so times 1/5 minus 1. That's basically -5 over 20. -5 over 20 is multiplication. So -5 over 20 minus 1, or -1/4 minus 1, which is -5/4. Last one, example 15. I just need to replace all the x with 0. So I see x here, I see x here. So 3 times 0 plus 1, and 0 minus 1 on the bottom. So it's 0 plus 1, so 1 on the top, and the bottom 0 minus 1 is -1. 1 over -1 is -1. That's example 15. And that is everything for 3.3. Thank you.